So now we're going to look at the major type of reactions that take place for conjugated systems, and we call these pericyclic reactions, and there's three major classes. So the first are what we call cycloaddition reactions. So in a cycloaddition reaction, you're adding together two different pi systems, and they're usually in separate molecules, but nothing says they couldn't be two different pi systems in the same giant molecule or something, but generally the ones we'll look at will be two different molecules, and we're going to add those together and form a ring from those. So it's cycloaddition. We're adding two pi systems to form a ring. The second type is called an electrocyclic reaction, and in this case we just have a single pi system, and we're either closing a ring like we're doing in this case, but it turns out they're completely reversible, so you can also open the ring. So they're just ring opening and ring closures. So, and then last but not least, we'll have the sigmatropic rearrangement, also involving just a single pi system. So, and generally what you're going to do is you're going to be breaking one sigma bond and then making one sigma bond in the process. And so the sigma bond that you've got ends up changing location. So that's kind of the nature of the name sigmatropic rearrangement. So we'll start off talking about what's called the Diels-Alder reaction, which is a certain type of cycloaddition reaction, but by far the most commonly studied of the different pericyclic reactions. So the most commonly studied pericyclic reaction are what's known as a Diels-Alder reaction. And a Diels-Alder reaction is just a specific cycloaddition reaction. So specifically we call it a 4+2 cycloaddition. The reason we call it that is that one of your pi systems either has 4 atoms or 4 pi electrons involved more recently is kind of how we look at it. And then the other one is going to have 2. And there's where the 4+2 cycloaddition comes from. In this case, we do call it a cycloaddition because we are going to form a ring, and Diels-Alder reactions always form a 6-membered ring specifically. It is a synaddition between two players, a Dynophile and a conjugated diene. So notice here's your diene. I got 1,3-butadiene in this case, and then your simplest Dynophile is just simply ethylene, and we can get a little more complex from there. But this is the most basic Diels-Alder reaction, and notice just the cyclic motion of electrons here. So you're breaking 3 pi bonds, and you're only moving one of them, so you only end up with 1 pi bond, but you've made 2 brand new sigma bonds in the process of making that ring. So now we're going to take a little closer look at the players involved in your Diels-Alder reaction, and it involves both dienes and dienophiles, and we're going to focus on the dienes first. So when we say that the diene must be in the S-cis conformation, and that should be a new term to you here, and so there's S-cis and there's S-trans, and the S stands for single bond. So normally we talk about cis and trans around alkenes. Well, here we're just rotating a single bond. And so if you look at like 1,3-butadiene here, so we're talking about the rotation of that single sigma bond in between them. And so if that bond is allowed to rotate around, we could have possibly this conformation as well. Now a single bond, as long as it's not part of a ring, is just free to rotate most of the time. There might be some effects on steric hindrance and stuff like that, but it's just free to rotate. And so we just say it's cis and trans around that single bond, and that's what S-cis and S-trans correspond to. Now for the Diels-Alder reaction to take place, your diene must be in this S-cis conformation. Anything that hinders its formation is going to slow the Diels-Alder reaction down. Anything that promotes its conformation is going to speed a Diels-Alder reaction up. And so based on that, first question we're going to answer here is I've got 5 dienes on the board, and we're going to talk about their order of decreasing activity in a Diels-Alder reaction. So again, we talked about anything that promotes the S-trans or inhibits the S-cis slows it down. Anything that promotes the S-cis or inhibits the S-trans speeds it up. So if I want the most here, so we've got a couple of ring structures, and that's important because here the sigma bonds in between the pi bonds are both parts of a ring, and that means they're not free to rotate. So if they're not already S-cis, they're never going to be. So well, this one here is S-cis, whereas this one here is S-trans. So this one that's S-trans, it's never going to get to be S-cis, and it turns out that this one doesn't do Diels-Alder at all. Therefore, I'm going to give him a ranking of number 5. So he's going to be the slowest in a Diels-Alder reaction by far. Whereas this one here, this one's essentially locked in the S-cis conformation and is going to do Diels-Alder very rapidly. In fact, it'll often do Diels-Alder reactions with itself in solution and stuff like this. And so he's definitely number 1. Now the other 3, they're not cyclic, so they're not going to be locked either S-cis or S-trans. So they're not going to be as fast as this one or as slow as this one, which won't even work. But we can look at some different factors which will affect how fast they react, and it comes down to where these hydrogens are relative to the methyl groups that are on these carbons. So here we've got a couple of hydrogens, So, and then here's a hydrogen, and here's a hydrogen. So, and the idea is that the two groups that point in here, so this hydrogen, and in this case, this methyl group, are bumping into each other. And I'd rather have two hydrogens bumping into each other than a methyl and a hydrogen, but I'd rather have a methyl and a hydrogen than straight up two methyl groups bumping into each other. So it turns out this one, the S-cis, would actually be very difficult to form as a result of just the steric hindrance of these two methyl groups bumping into each other. And so as a result, this is going to be the next slowest one coming in at 4, then this one at 3, and then this one, the least steric hindrance, when the S-cis conformation forms, will come in at number 2. So we're looking at steric hindrance, or in some cases, whether a ring either locks it in the S-cis or locks it in the S-trans conformation here. The other factor for dienes is that we find out that when an electron donating group is attached to the diene, it's going to speed up the reaction. So it turns out we'll find out a little bit that we view the diene as kind of the nucleophile in these reactions. So, and if you raise the energy of the electrons in a nucleophile, you make it more reactive, and you do that by having electron donating groups attached. And so in this case, I've given this diagram we learned about in the alcohol chapter about what are the different electron donating and electron withdrawing groups, and we'll kind of look at them there. So in this case, we've got a methyl group right there. In this one, we've just got hydrogens, and in this one, we've got this OCH3, and your OCH3 is this guy right here, and that's a strong electron donating group, whereas your methyl group is just a plain old R group, an alkyl group, so, and it's kind of a weak electron donating group, and then you've just got hydrogens, and that's going to give you your order of reactivity right there. So your strongest donating group is going to be number 1, then your next strongest donating group number 2, and then with no donating groups, just hydrogens, it's going to be number 3. And that's your decreasing order of reactivity in the Diels-Alder reaction. So now we'll take a look at the Dienophile, and for the Dienophile, it's exactly the opposite in terms of electron donating, electron withdrawing as it was for the diene. So now we actually want electron withdrawing groups, as they're going to make the Dienophile more reactive. So just like we said a little bit ago, we said the diene, we usually view him as the nucleophile, and electron donating groups make that more reactive. But the Dienophile we therefore view as the electrophile, and it's withdrawing groups that make it more reactive. They lower the energy of the LUMO, the empty orbital we're going to accept electrons into. And so in this case, if you look at the cyano groups, those are electron withdrawing groups. And so having the greatest number of electron withdrawing groups, this would be the fastest in a Diels-Alder reaction, and then second, and then with no withdrawing groups, that would be third.